It's Wednesday, August 19th, and we're recording for introductory chemistry. All right, I'm going to take over the screen. And the first thing we're going to do is take a look. So what we're going to talk about today is the periodic table. Okay, and we're going to specifically talk about 7 different ways. I believe it's 7 different ways to classify the elements on the periodic table. Okay, again, for those of you that were with me at the high school, you've seen this all before, the exact same material. Okay, so first off, we should ask ourselves, why is it called the periodic table? Okay, and it's called the periodic table. Well, let's ask this question. What does the word periodic mean? Anybody remember? What does the word periodic mean? Nobody remembers. What's that little dot called at the end of every sentence?
Period.
A period. All right. So, and what's a woman's menstrual cycle? What's another name for that? You have your
period.
Period. So why is it called that? Right? Why is it called that?
It's the end.
Because it occurs at regular intervals.
Oh, okay.
All right. It's something that occurs at regular intervals. So this word periodic literally means occurring at regular intervals. If some of you, I don't know how much math some of you have taken, but you may, if you go far enough in math, you'll cover periodic functions, like sines and cosines are periodic functions. The values of the functions repeat themselves at regular intervals. So your birthday, for example, is periodic. If today is your birthday, 365 days from now, you're going to have another birthday. Another 365 days, another birthday. Notice the interval is exactly the same. Days of the week are periodic. Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and I'll bet the next day is another Sunday. 7 more days after that, another Sunday. Another 7 days, another Sunday. So there's many, many things that are periodic. Do not make the mistake of thinking that that interval has to be a time interval. It need not be a time interval. For example, that little dot at the end of darn near every sentence, that has nothing to do with time, right? That has nothing to do with time. Certainly the periodic table has nothing to do with time. Element 22, if you have a periodic table in front of you, element 22, Ti, that the Ti does not stand for time, it stands for titanium. So, but in our studies here, and we'll probably see the first one today, we're going to be looking for certain properties of the elements that repeat themselves on a regular basis on the periodic table. We should see one today. All right. Now, when was the periodic table invented? It was invented by a guy named Dmitri Mendeleev. Let me open my brand new markers. Man by the name of Dmitri Mendeleev. And if you do have a book, this is all in like chapter 4 or so. Okay? So this was around like 1867 or so. And some books say 1865, some say 1867. All right, so he was a Russian chemist. And this was a major, major discovery, him coming up with the periodic table. We should also understand that at the time that Mendeleev came up with the periodic table, there were only on the order of around 65 known elements. So a little over half of the elements were known at the time he came up with the periodic table. So how did he make the periodic table if roughly half of the elements were missing? Well, he left missing elements on the periodic table. He said, I know there's an element that belongs here, but it just hasn't been discovered yet. That's a very powerful test of a scientific theory, is you can make predictions about things that have not yet happened or been discovered. And so he made predictions about many, many elements. He said, I know this element exists. Scientists just have not discovered it yet. So once he did that, and the periodic table was accepted, there was a mad dash to go off and discover these elements that he had predicted. And sure enough, in due time, one by one, the elements were discovered. And they had the properties that Mendeleev had predicted that these new elements would have. Okay? So again, that's a very powerful test of a scientific theory. Anybody has a question at any time, please do not hesitate to stop and ask. Please do not hesitate to stop and ask. All right, let's see, I just see somebody else joined us here. Okay, so I'm going to take over the screen here and we're going to do the first classification of the elements. Okay, so here it is, right? So this is what's called the block classification, B-L-O-C-K. So there's 4 blocks. I have them color-coded on this periodic table. 4 blocks. In green, we have S block, S as in Samantha, right? S block, S as in Samantha. Okay? In yellow, we have P block, P as in Pedro, P as in Pedro. So we have S block and P block. Okay? In blue, we have D block, D as in David, D as in David. And down on the bottom in the off orange, we have what is referred to as F block, F as in Francine. Right? F as in Francine. Does everybody have that?
Got it.
So there's our first classification, S, P, D, and F blocks. All right? Now, again, with any collection of objects, where our collection of objects are the 118 chemical elements on the periodic table, you can always classify them in a different number of ways. For example, the registrar might be, one way the registrar might categorize the people in our class is instructor and students, or maybe male and female, maybe people that are receiving financial aid, people not receiving financial aid, what town you live in, right? There's always different ways to categorize the objects in a collection of objects. So we have our first classification here, the block. We can just say, what block is, notice, each of the 118 elements fits into one of these 4 blocks, right? Fits into one of these 4 blocks. Now, oh, where's my eraser at? Oh, I left it out in the car. There we go, that'll work. Now, what's the second way to classify the elements? Okay, and I'm gonna write it, hopefully you'll be able to see my little screen here. If not, I'll unshare and you'll be able to see it. A second way to classify the elements is whether they are representative Can people see that, or should I put it on the full screen?
You should probably put it on the full screen.
Full screen? Okay.
Or wait, we can switch between screens, I think, if we click on the smaller screen. Yeah, and we can switch
Oh, and
between
just pin it, yeah.
in my computer anyway.
Just trying to remember how you. Where's my controls at? Meeting control. Oh, here we go. Stop share. Up at the, for some reason it's up at the top. Okay, so representative elements and transition elements. Okay, so every element is either representative or transition. It is very easy. Very easy. The representative elements are S and P block. S and P block. Okay, and the transition elements are D and F block. So the blue and the orange, and I can't remember what color the S was, but the P was yellow. Okay?
Got it.
So sometimes we only need to know, is an element representative or transition? That's all we need to know. But sometimes we need to know what block it's in, right? So we have these two different classifications. Any questions there? Any questions? All right. A third way to classify the elements is whether or not they occur in nature naturally. And this is not really so important, but as long as we're talking about the elements, it's worthwhile to mention it. There's some argument over exactly which elements, how many of the elements occur in nature. Usually I say 92, up to uranium, number 92. And we'll continue with that. We'll say 92. But I should mention that plutonium number 94 has been discovered in very small quantities naturally on Earth. They use plutonium to make nuclear bombs, but they make the plutonium. They don't mine it. And recently in some very, very large stars that have exploded, they have detected some of these other elements way beyond uranium, like curium and berkelium and californium, even einsteinium. Those have been detected in massive, massive stars that have exploded. So we will consider them as not occurring in nature. Again, this is not a crucial thing. Okay, so we'll go with 92, uranium, because that's a nice, easy one to remember. Everyone's heard of uranium. Uranium and plutonium, for most people, are the only two elements they've ever heard of down in F block, down on the bottom in the orange. Okay? Any questions there? Again, sometimes all we need to know, representative or transition. Other times, we need to know not just representative, but whether it's an S block or P block. Similarly with transition. Won't be good enough just to say transition, but is it a transition D block or a transition F block? Okay? All right, so there's three classifications we have right now. SP, D, or F block, representative or transition, and whether or not the element occurs in nature. Okay? Let's see. So let me bring up the next one. All right, so here we have, there we go. All right, so here we have the elements arranged according to whether they're metals or non-metals. So in the blue, can you guys can see my red cursor, right? You can see my red cursor moving?
I can see your,
okay.
It's not red for me, it's white, but I can see.
All right, so so in blue, we have the metal elements, and we can see that the vast, vast majority of the elements on the periodic table are metals. The vast, vast majority of the elements are metals. Okay? You notice even over here, number 20, which is calcium, which is what our bones are made out of, right? Is a metal element. So you can think of your bones as actually being made out of metals. All right, although most people probably wouldn't say that, but they are made out of calcium, and calcium is a metal element. Okay, over here in the yellow, we have the nonmetals. Okay, and notice all the nonmetals are clustered together in the upper right-hand corner, except for over here, the very first element, hydrogen. Right, except for the very first element, hydrogen. Right? Maybe kind of wonder why hydrogen is not over here next to helium, but there's reasons for it that will, yeah, I did record
Atomic
this,
weight.
that we'll talk about later. Okay, any questions so far? Now, how about in the orange there? Who drew that? Who drew that line there? That wasn't me.
Doesn't mean.
How did you do that?
Me. I apologize.
How did you do that?
I just I have the marker on, I guess, the pen.
Oh, okay. I didn't think you could do it if I was doing the presentation. Okay.
Shit. Shoot.
Well, in orange there, I'll tell you what, I'll unshare and then bring it back up again. This one is the one we want. Okay, there we go. So in the orange, we have what are called metalloids. Metalloids. So metal, and then L-O-I-D-S at the end. Metal, and then loids. Okay, so what are metalloids? Metalloids are kind of, some of their properties are like metals, and some of their properties are like non-metals. Okay, and there's some very, very important metalloids. For example, silicon and germanium. Without those, we wouldn't be here having this class right now, because that's what computer chips are made out of. Computer chips are largely made out of silicon, doped occasionally with germanium atoms. Right, so every computer chip is made out of that. Okay, so there are some very, very important metalloids. Arsenic is rather important. The other ones, not so much. Now, I will mention that with these new elements down here, like 113 up to 118, if you look at different places on the internet, you'll see them classified differently. Notice I left 118, the very last element here, okay, organesson. I left that one, I didn't classify it. And that's because I looked at some places on the internet, they said it was a metal, other places they said it was a gas. All right, and how is it they don't know? Well, there's only ever been a few atoms, less than 10 atoms, I believe, of that element ever made. We should mention, we said only the first 92 elements occur in nature. So where do the other ones, the 93 through 118, where do they come from? Scientists make them in the laboratory. They're made by scientists in the laboratory. Okay? So again, especially when you get up here like above 110, I mean, most of those, only a few atoms have ever been made. They don't last very long. They're radioactive and they decay really fast in some cases. A few compounds have been made of some of these, but no compounds have been made of element 118. So this prediction that it's gas has come about from calculations. Right? No one has observed it to be gas. Other calculations have suggested that it's a metal. Right? So again, if you see that, it's the same with here with number 85, astatine. In some places, I think maybe even in our textbook, it may say that astatine is a metalloid. So how many metalloids there are is open to discussion, right? That's open to discussion. But these six here, the first six metalloids, pretty much everyone says those are metalloids. Now, this begs the question. We said that most of the elements are metals. We have some non-metals in the yellow and a handful of metalloids. I'm not going to be too concerned about the metalloids. I do want to mention, though, I don't know how you turned that pen on, but if you were to put your, I lost my cursor, but if you were to put a pen here and like draw a line down to here, all right, if the element lies on that line, it's a metalloid. If it's to the left, it's a metal except for hydrogen, all right? It's a metal except for hydrogen. And if it's to the right, it's a non-metal, right? It's a non-metal, okay? So again, this is actually, what's going on here? This is actually a very important classification, the metals versus non-metals. But this begs the question, what is a metal? What's the difference between a metal and a non-metal? Does anybody know?
Shininess, weight.
What was the second thing you said?
Weight.
Weight? Nah, not weight.
Not weight? Okay.
Shininess, yes. Most elements that are shiny are metals. You're right, whoever said that.
Mhm.
But not all metals are shiny, right? But if an element is shiny, it's pretty much guaranteed that it's a metal. Let's see. I have samples of about 45 or 50 elements. Okay, so let's take a look at some of these. I'm gonna unshare here. So there's something shiny there, right? Can you see that that's shiny?
Mm-hmm.
So that's aluminum, bright and shiny. All right, here's platinum, which is worth more than gold, bright and shiny. All right.
Mm-hmm.
Here's palladium, which also is worth more than gold. Can you guys see these?
I can see them.
Yeah.
Okay.
It's
It's,
cool.
you know, I wish I could use my high school laptop, but we don't have Zoom loaded on it, and I can't do it, I don't think. Now here's selenium, which is a metalloid. Selenium. Notice it's not bright and shiny. It's kind of dark gray, right?
Mm-hmm.
And then here we have antimony, antimony, which also is not very shiny. It's kind of an off grayish color, these little pellets. Okay, so whoever said that metals are bright and shiny, that's true to a big extent, but not always true. But here's silver, which is bright and shiny. All right, bright and shiny, it's a metal. Here's titanium, which is not very shiny. Is not very shiny. All right, and here is niobium, which is another metal. I think it's number 41. Is that right? Yeah, 41. Right, not very shiny at all. Not very, a little bit, but not like silver or the palladium. Right?
Mm-hmm.
So, but that's not, but those are properties of metals, that metals are shiny and non-metals are not. Those are properties. That's not a defining feature of what a metal is and what a non-metal is not. All right, the defining property, and you should write this down. So here's a question. What's the difference between a metal and a non-metal? Let's write that down. What's the difference between a metal and a non-metal? All right, and we'll give the answer here in a moment. What's the difference between a metal and a non-metal? You're going to be asked this. Okay? Metals conduct electricity and heat. Metals are good conductors of electricity and heat. You have copper in wire, right? To conduct electricity. Metals are good conductors of electricity and heat. Non-metals are not. Non-metals are not. What's the opposite of a conductor? If something's not a conductor, it's called an
insulator.
An insulator. Very good, whoever said that. So non-metals are insulators. Metals are conductors of electricity and heat. Non-metals are not. Metalloids are kind of in between. In between. Okay? Again, metalloids,
Okay.
some of their properties are like metals, other of their properties are like non-metals. Okay, any questions? And again, This distinction for metalloids, you don't need to memorize the metalloids. I will give you some elements and say, here, let's bring the periodic table back up again. You know, if I give you some elements and say, all right, which one is a metalloid? I'm not going to give you like gallium here, gallium and arsenic and selenium. You know, I'll give you, say, like germanium and maybe something over here, molybdenum, something over here like fluorine. So you won't even, it'll be very obvious. It should be very obvious to you. Again, if you draw this line from the lower right-hand corner of boron down here to the upper right-hand corner of polonium, that lies on that line, it's a metalloid. If it's off the line to the left, it's a metal except for hydrogen, the very first element. If it's in the upper right-hand corner, if it's to the right of that line, it's a non-metal. Okay? All right, any questions so far? So let's count how many ways we have to classify the elements so far. Block, S, P, D, or F. Representative versus transition. Whether or not the element occurs in nature is the third way. And the fourth way is metal versus non-metal and metalloid. Right? Metal versus non-metal and metalloid. Generally, we think of metals and non-metal. Right? And you're just going to classify them that way. The metalloids would come under the non-metals. Right? Any questions? Just a lot of information, but it's none of it by itself is very difficult. Okay, so while we have this up, let's look at another classification. Okay, and notice down the left-hand column, or sorry, down the left-hand side of the periodic table, we have the Arabic numerals 1 through 7, right? And these correspond to the rows on the periodic table. So every element is in a row, 1 through 7. Okay, the rows are actually called periods. Periods. Right, so every element has a period number, 1 through 7. Okay?
Okay.
Periods. So the periods are down the left-hand side, and what are the numbers we use every day are called Arabic numerals, the way that we write them. Right? 1 through 7. And they correspond to the rows, R-O-W-S, the rows on the periodic table, right? So for example, here, like technetium number 43 is in period 5. Anybody want to take a stab at what period uranium? Look down at the very bottom. Uh-oh, I'm getting a message that my internet connection is unstable. So if I lose you here, just be patient. All right. So down here, number 92, uranium. Anybody have any idea what period that is?
Period 7.
Period 7. Very good. How about here, number 64, gadolinium? What period is that?
Period 6.
Period 6. Very good. If you again, is my arrow, is this red arrow showing up? Can everybody see it? Please speak up if you cannot see it. Everybody can see it. Okay, otherwise I'll unshare and I'll hold up a periodic table. All right, so if we take a look here, if you notice, the elements are numbered consecutively. We haven't spoken about those numbers yet. We started hydrogen, number 1, over here, helium 2, then in period 2, 3 through 10, period 3, 11 through 18. But if we look down here at period 6, it goes 55, 56, 57, and then 72. What on earth happened to 58 through 71? They're down here in F block in the lanthanide series, 58 through 71. 58 through 71. So notice there's a thick black line here that I made on this periodic table, and a thick black line here. So this entire lanthanide series, 58 through 71, fits up here between 57 and 72. All right, does everybody see what I'm talking about there? Similarly, in period 7, it goes 87, 88, 89, 104. What happened to 90 through 103? Down here, the actinide series. 90 through 103. If you're wondering why they're called the lanthanide and actinide series, it's because the element previous to them, number 57, is lanthanum. So 58 through 71 is the lanthanides. Here we have actinium, so the elements that follow it, the next 14 elements, are referred to as the actinide series. But the entire actinide series, 90 through 103, fits in this bold, this thick black line here between actinium and rutherfordium. Okay, any questions? So we can, in fact, assign a period number to every element on the periodic table, even those down in F block that seemingly, at first glance, seemingly have no period numbers whatsoever. Okay, any questions?
Got it.
So now we have 5 ways to classify the periodic table. Block, SP, D, or F, representative transition, whether or not they occur in nature, metal versus non-metal versus metalloid, and now we have period number, Okay, well, we can see that this is, periodic table is kind of set up as a grid. So if every element has a row number or a period number, every element should also have a column number. And we see that there's actually 2 sets of column numbers. Okay, for right now, let's focus on the Arabic numerals, 1, 2, 3, 4, 5, all the way up to 18. All right, so there's 18 columns on the periodic table. So those are referred to as groups, G-R-O-U-P-S, group. So people say, what's the group number? What's the group number? Okay, so every element has, for the ones down in F block, you may ask, what group is, say, uranium in? I'm never going to ask you that because it's not so obvious. All right, but I'll never ask you for a group number down in F block. All right.
All right.
Somebody had a question or comment? Okay.
No question.
Sorry? No question?
No question.
Okay, thank you. So again, every element has a group number 1 through 18. Let's see, what else did I want to say? You may notice if you're reading on the internet or maybe your textbook, the groups, the columns are, some people will call them families, although group is far and away the more predominant term. Group or family, and of course the periods are the rows. Okay? All right, any questions? So now we have the 6th way, We'll get to these Roman numerals up here on top in a moment. All right, we'll get to those in a moment. Now, there's one last way, a 7th way to classify the elements. Is it 6 so far? Block, representative transition, naturally occurring, metal versus metalloid, and yes, 5th is the period number, and 6th is the group number. Oh, yes, I know what I wanted to say. Some books, or maybe some places on the internet, they may use the term getting another unstable connection signal. You will see the term main group. I think our textbook actually uses the term main group interchangeably with representative. Okay, so just be aware of that. Okay, you might want to jot that down in your notes somewhere. Main group is also called by some people the main group elements, which is S and P block. S and P block. If you guys want, I can email you these colored periodic table versions. So you'll have these to look at, especially for those of you without a textbook. Okay? So now we have the 6th way.
I have a question. Would you be able to explain the 6th way again? Because my connection completely lagged and I didn't get that.
Send the what? Oh, say
if I
what?
could get if I could get the explanation how to classify the elements the 6th way again, because my internet lagged and I couldn't see it. I couldn't hear it.
Just run down the 6 ways?
Yeah, no, the 6th way, just the last one.
The 6th way is the column numbers. You see here we have
column
column 1, column 2, all the way up to column 18.
Correct.
Right? So columns 1 up to column 18.
Mm-hmm.
Is that clear now? So if we look at,
Yeah,
say,
that's clear.
aluminum here, for example, aluminum is in period 3, and group 13.
13.
Okay, if we
Okay.
look at polonium, polonium is in period 6 and group 16. Okay? All right.
Okay.
We good there? Okay. So now let's look at the 7th way. This is our last way to classify the elements. I'm going to stop sharing and bring up this other way. Now this is an important one also. Okay, so notice I have 4 of the groups colored. 4 of the groups colored. All right? But before we talk about this, let's talk about these Roman numerals. Because of these 4 groups that are colored, I generally think of them in terms of the Roman numerals rather than 1 and 2 and 17 and 18. You should be familiar with them both ways. And it's kind of easy to remember because they're at the 2 extreme ends of the periodic table, right? To the far left or the far right, right? And so I like to call these, let's write these down and then I'll bring that back up again. I call these group, it's just a term I made up myself. Group classifications, they're kind of like nicknames. Group classifications. So group 1, and then in parentheses, in black, I'm going to put the Roman numeral 1A, all right, 2A, and 7A, and 8A. Does everybody know their Roman numerals?
Mm-hmm.
So this is group 2, group 17, and group 18. Okay? And
Got it.
Get a different color here. So group 1, or Roman numeral group 1A, is called the alkali metals. Alkali metals. Notice that does not include hydrogen because hydrogen is not a metal. Quite often students will screw that up. I'll say give like 5 or 6 elements and I'll say circle the elements that are alkali metals and people will circle hydrogen. Hydrogen is a gas, it's not a metal. Although if you pull it down to about minus 450 degrees, it does become a metal. Let's see, group number 2, is called the alkaline earth elements. And notice that every alkaline earth is a metal element. Well, actually, we'll bring that up when we put the periodic table back. Where have you heard these 2 terms, alkali and alkaline, before in everyday life?
Batteries.
Batteries.
Yes.
Batteries. Right? You may have some health nuts say that alkaline water is good for you. I have a guy over at Smith's trying to sell me alkaline water for a bunch of money. Just how?
At least we're still not drinking radium.
Yeah, that's true. Okay, number 7 is called the halogens. The halogens. Where have you heard that word?
Lamps.
Lamps or headlights on cars. If you're driving at night and you're like blinded by someone, sometimes I'll flash my high beams at them because I think the other car has their high beams on, but they don't. They just have halogen God, I just said it a moment. What's the word for the headlights? Headlights. They have halogen headlights. They're much, much brighter than regular headlights. And then finally, group 8 actually has 2 nicknames. 2 nicknames. They're called the inert gases. Inert gases. And the other nickname is the noble gases. It was only a year or two ago that I actually got motivated enough to search on the internet, why are they called the noble gases? So we'll get into that. Generally, you'll hear me call them the inert gases. It's the more scientific term. Okay? Does everybody have those?
Got it.
All right, I'm going to bring up that periodic table that has the colors now. So here we go. All right. So, again, the inert gases. Again, I have included 118, although it's kind of still up in the air as to whether 118 is a gas. Some people will say it's a solid. But we will include it for the sake of simplicity. We'll call it a noble gas. Right? We'll consider it to be a gas element. Okay? One thing that the inert gases, they're very easy to spot. Even if you don't have a periodic table in front of you, they all end with ON except for helium. They all end with ON except for helium. There's only 3 other elements that end in ON on the periodic table. Number 6 carbon, number 26 iron, and number 14 silicon. Other than those 3, if an element ends in ON, it's guaranteed to be an inert gas. Okay? What does the word inert mean? So now you have your...
They have no effect or...
No what?
No effect. I remember being explained this, like with welding, they use a certain gas because it doesn't create an explosion with fire or something
Jasmine
like that.
joined us. When did you join, Jasmine? You have the right idea. Somebody do a little better though. Inert.
Yeah, it's a non-reactive. They do not react with other elements.
Yes, very good. Unreactive. Unreactive or unable to move. Unreactive or unable to move. Either, and later in the course we'll find out what is unable to move. Okay, because there is something that's unable to move on the inert gases. We'll find out what that is later. Right, but they are all unreactive. Apparently this number 118 is a little different. It is reactive. Some people even say highly reactive. But again, that's kind of hard to say. Only a few atoms of it have ever been observed. Okay, but the rest of these are very, very unreactive. In 1964, so if they're unreactive, that means they don't form compounds. They're found in nature by themselves. You never see argon or neon combined with some other element to form a compound. And again, in 1964, I believe it was, the very, very first compound was ever made by chemists in a laboratory that contained an inert gas. I believe it was xenon difluoride, XEF2. And it was a big deal because up until then, scientists believed that they could never, ever form a compound. But again, in nature, they don't form compounds. But by now, several hundreds of compounds have been made by scientists in the laboratory that contain an inert gas element, right? Several hundred of them, right? But none of them are found in nature. So why are they also called the noble gases? Now, I do want you to know that definition for inert. So you have two definitions so far today. Periodic, right, occurring at regular intervals, okay? And inert, which is unreactive or unable to move. 2 definitions that I want you to know. Right? Now, you don't need to know why they're called noble gases, but since I did spend the time to look it up a couple years ago, I'm going to go ahead and say it. Several hundred years ago in Europe, the nobility, the dukes and the duchesses and whatever, the knights, they were called the noble class of society, right? And they did not mingle. They did not mingle with the lowlifes, the common folk like us, right? They were lofty. They kept to themselves. They did not interact with the common folk, the peasants, so to speak, right? So that's just like the inert gases. They don't interact with the other elements on the periodic table. They keep to themselves. This is where the term noble gas came from, right? But again, you don't need to know that.
Mhm.
You don't need to know that, right? Sorry for referring to, if anybody took offense to me calling them common folk or peasants, right? I'm one of them also, right? I don't know, maybe some of you are of the noble class, right? But I didn't mean to offend anybody. Got to be careful in this day and age, right? All right, so are we good here? Now, again, did anybody see a mistake I made? Anybody see a mistake I made?
Mm,
I did make a mistake.
Is it hydrogen?
Hydrogen should not be colored. Hydrogen should not be colored there. I'm trying to think what to do. I actually made this just like I was over at the high school and I made these periodic tables, the colored versions, real quick before I came home. And I did not mean to color hydrogen. Right? So please correct that. Remember, hydrogen is a non-metal. So it cannot be an alkali metal. It's a non-metal. Glad I caught that. Very good for whoever else caught that. Okay? So now, you are going to be asked at times, which element, you're going to be given a list of elements. I'm going to say circle the alkaline metal or circle the alkaline earth. Now, again, I'm going to give you a little bit of advice here. Easy way to remember this. Very, very easy to remember. Remember, it's the two groups on the extreme left and the two groups on the extreme right of the periodic table. Right? So that's the first thing to remember. That's very easy. And then if we look up here, if you write them out, they're in alphabetical order. They're in alphabetical order. So these are the two on the extreme left and the two on the extreme right. So very, very easy. And you should recognize alkali comes before alkaline alphabetically. Right? Comes before alkaline alphabetically. Okay, so very, very easy to remember. And that's even true whether or not you call them inner gas or noble gas. But you will almost always hear me say inner gas. Occasionally, you'll hear me say noble gas. Okay? Let's see here. Any other questions so far? So there's our 7 ways to classify the elements. Any questions? It's pretty straightforward so far. Pretty straightforward. I'm going to bring a periodic table up. I'm going to bring up, I kind of like this colored version. Cheers me up. Now, we haven't talked about these Roman numerals yet. We will in a moment. But let's talk about a few other things here. Okay? We said that for each element. Okay? Now, again, this is a very stripped down version of the periodic table. For each element, there's 4 things. There's a number on top. What's that number called? Anybody remember?
It's the atomic number.
The atomic number. And notice the atomic number is used, the elements on their periodic table are arranged according to increasing atomic number. Write that down. That's very, very important. That's one of the more important things we have said today. Okay? How are the elements arranged on the periodic table? In order of increasing atomic number. I'm going to turn the fan on here. It's getting, I guess I can't get over it. But they are arranged by order of increasing atomic number. Now, I will tell you, the idea for atomic numbers didn't come about till around 1911 or 1912. A guy by the name of Michael Moseley came up with the idea of atomic number. Actually, Mendeleev had the elements arranged by order of increasing atomic mass. So if you look, for example, at numbers 51 and 52, 52 and 53, he had those flipped. He had them by order of increasing atomic mass. And as you go from one element to the next, the mass generally does get bigger. there's two cases. Those, and somewhere in D block, there's, but Mendeleev had them in the wrong order, and it was like that for about 50 years. Then a young guy, real young guy, I think he was in his late 20s, came along, and he came up, did the photoelectron spectra of all the elements known at that time, and put them in the proper order. It's kind of a shame he was killed in battle in World War I. Real young scientist, very, very smart guy. It was a shame he was life ended early. Now, so again, Mendeleev had no idea of atomic numbers, right? So there's the first thing. And the atomic number is equal to what? For a given element, the atomic number is equal to what? This is going to be the single most important thing we have said today so far.
Isn't it the number?
It's equal to the number of
Equal to the number of, and then you got cut off, whoever said that.
Protons.
Yes. The atomic number is extremely important. It is equal to the number of protons in every atom of that element. So even when Michael Moseley came up with the idea of atomic number, he knew nothing about protons. Protons were discovered another year or two later. Okay? So how do you know which element an atom belongs to? Here's the question. How do you know which element an atom belongs to? By the number of protons that that atom contains. Because the number of protons is equal to the atomic number for that element. Number of protons is equal to the atomic number for that element. So if you walk into a room and you see an atom sitting on a table, and I say, Antonio, what element does that atom belong to? And you look and you count the number of protons, and you say, well, Raymond, there's 50 protons there. Therefore, it must be a tin atom, because tin's atomic number is 50. Okay? If I say, let's see. If I say, Stephanie, what element does your atom belong to? And you say, well, Raymond, I count 20 protons. Therefore, it must be a calcium atom, because calcium's atomic number is 20. That is the single most important thing we have said today. Make absolutely certain you know it. What determines the element to which an atom belongs? The number of protons, not the atomic number. The atomic number is an abstract concept. It's an abstract concept. All right, when you look at an atom, you don't see atomic number, you see protons. You see protons, all right? And the number of protons is equal to the atomic number. All right, everybody clear on that? You should put a box around that with stars. That's the single most important thing we have said today. All right, put a box around that with stars. What determines the element to which a given atom belongs? Number of protons that it contains. Okay? So we see now the periodic table is pretty much complete, right? Pretty much complete, because every period number is complete all the way over to group number 18. All right. So what's the second thing in this little box for any element? Let's look at carbon now. So then we have C, right, which is the chemical symbol or the element symbol for that element. Now, listen to what I'm saying here. Notice the element symbol is either one letter or two letters. One letter or two letters. Okay? The first letter is always uppercase, capital letter. The first letter is always uppercase. The second letter, if there is one, is always lowercase. The second letter, if there is one, is always lowercase. This is very important. I will mark you wrong. Let me unshare here for a moment. So let's look at what I mean by that. There's cobalt, number, what is it, 27 or so. All right, cobalt. This is carbon monoxide. You could put this in your mouth, roll your tongue over it. It's a relatively inert metal. This carbon monoxide gas, I think you know, comes out your car's exhaust pipe. It will kill you. it will kill you. Right? So a deadly gas, a relatively inert metal. The only difference as we've written it, lowercase o, uppercase o. So again, and don't tell me, here, let's pick one. What element is that?
Is that sodium? No.
Doesn't look like sodium to me.
No, I forgot what Na is.
There is
it
no such
potassium?
element.
Oh God.
There is no such element.
No,
This is sodium.
I'm lost.
Notice the second letter has to be lowercase.
Oh yeah.
That's a capital A.
Lowercase,
I
I
just
get it.
wrote it small. I just wrote
Yeah.
it small, but it's still a capital A. Okay, somebody. Okay, it's still a capital A. Why did the chat come up again? All right. Does everybody understand what I'm saying? Don't
Yeah.
write it small and still a capital letter. I'm going to mark it wrong. All right. So no such element, sodium. All right.
Yeah.
Okay. Let's bring that periodic table back up again. The second letter is always lowercase if there is one. Then we have the third thing, the name of the element. All right, simple enough. But let's look at the fourth thing, which is the atomic mass. The atomic mass. Okay? We'll talk more about atomic masses later in the class, but for another week or two, maybe 2 weeks. We'll see where these atomic masses come from. But for right now, just suffice for us to know that the bottom number is the atomic mass. Now listen to me. If I ask you for the atomic mass of, say, carbon, don't tell me 12. It's 12.011. All right, if I ask you for the atomic mass of cobalt, don't say 59. You're not to round these masses. Does everybody understand that?
Mm-hmm.
All right, everybody understands that. And I want you to use my periodic table. These are the most recent values for accepted values for the atomic masses on the periodic table. Right, so I want everybody using the same periodic table. So because different periodic tables will have slightly different values for the atomic masses. And do not round them. That's the more important thing. Do not round them to the like nearest whole number. For one thing I've discovered over the years, a lot of people don't know how to round. Let's look at over here, number 11, that's sodium. This is a classic one. I've seen this mistake made quite a few times. If you were to round the atomic mass of sodium to the nearest whole number, what is it?
23.
23. You would not believe how many people write 22. You would not believe it. This is why I don't want you rounding the atomic masses. Okay? All right. Trying to think. I do want to give you an assignment. Now, some people got mad at me when this COVID stuff first happened in the second half of the spring semester, because they were turning assignments into me. I graded them, but I didn't have access to a printer. I do now. I can print at the high school. I've also found a place at Los Alamos. For 7 cents, I can go and print a page. Okay? So when you guys do your work, all right, if you don't have a scanner, you can take a picture of it and just email that back to me for the time being, right? We'll have to see how long. I'm going to be honest with you. I would prefer that we use my assignments. I'm kind of upset at the high school because we have to do assignments a different way now. Everybody has to do them with Google Classroom. My students who have been taking my class, Jasmine and Dre, and 2 or 3 more of you, you know I have all these assignments typed up already. And I have literally thousands of different assignments. I don't want to have to spend time making new assignments. So I will email you the assignment. You can, if you guys that don't have access to a printer, I don't know what you're going to do. There was only like 2 or 3 of you. Has Monique checked in yet? No Monique. How about Anita? So if the people logged in right now, it just looks like Jason and Stephanie don't have access to the printer. You might just have to handwrite it. You might just have to handwrite it and then take a picture with your phone and then email me back the picture that you've written. Okay, the first one, you may have to handwrite quite a bit of stuff, right? But don't panic. It won't be like every assignment will be as much where I have typed in as much as this first assignment. Okay, but you guys that don't have a printer, try to find someone that does have a printer. If not, you're going to have to handwrite it. Okay, and if you don't handwrite the question. Here, I'll show you what the first assignment. I'm going to say, we still need to get to these Roman numerals here. So I'm going to say, what's the atomic mass? I'm going to say, provide the atomic mass of each of the following elements. I'm going to have like carbon and a line, iron and a line. So if you don't have a printer, I'm going to ask you, you're going to have to write this and then the mass, this and then the mass, right? So you might have to do quite a bit of writing for the first assignment, but then after that, it won't be, only the first assignment of the course, I think, will be like that. Okay?
Mm-hmm.
But try to find access to a printer. I'm
Are you
sure
gonna
one of your buddies somewhere.
Are you gonna
has
send
a-
the assignment today?
Say again? We'll talk about
Are
that
you
later.
gonna send?
Yes, I will send it today.
And when does it do?
Well, let's talk about that later. All right, when I shut the
Okay.
recording off. Let's see. So let's bring back up that periodic table. Okay. So again, how are the elements arranged on the periodic table? In order of increasing atomic number. How do we know which element an atom belongs to? By the number of protons that it contains, right? By the number of protons that it contains. So those 2 things, you should have boxes around them with stars. The third thing you should have box around with stars is, what's the difference between a metal and a non-metal? Metals conduct electricity and heat, non-metals do not. You should have a box with stars around that, okay? You know, typically if we were in the classroom and we were talking about what's the difference between metals and non-metals, I always take out my keys. And I pick on someone and I give them my keys and I say, go put this key into the electrical outlet. All right? And, you know, a couple of semesters, someone has actually walked across the room to put it into the outlet. Those people will say no. And I'll say, why not? Because I'll get shocked. Why will you get shocked? Because the key's made of metal, they'll say. And, okay, so they conclude metals conduct electricity. Okay? All right. Now, we need to get to these Roman numerals here on top. The Roman numerals on top, right? They are actually very important. The first thing I want to point out to you is that the Roman numerals only appear for the representative elements. In other words, S block in the green and P block in the yellow. The Roman numerals only show up for S block and P block. All right. Oh, somebody's chatting. Are you wanting me to respond here? Where the heck happened to my chat? My chat has disappeared. If you were chatting towards me, just speak up.
Oh, yes, I was just mentioning I did have a class at 5:30.
Oh,
Yeah, me too. It's for intermediate algebra.
you have a
Mine's
class at
public
5?
speaking. 5:30.
Yeah, at 5:30.
What are you gonna do? We're supposed to have lab.
Not sure. I just thought I'd mention it.
So
Wait,
let
we
me
have
ask you
lab
this.
today?
But wait, I thought all of your other classes were on Blackboard.
Yeah, but some teachers are doing Zoom meetings.
Oh, some of them are doing Zoom meetings.
Yeah.
You know, you're supposed to have lab today at 6 o'clock.
Yeah,
At 6 o'clock. I work at 6 o'clock.
All right, well, here. Well, I mean, you got, okay, let's just say what these Roman numerals are and then we can finish. Okay, the Roman numerals, right, are only for S&P block. The Roman numerals
Only.
Actually, we got two more things to say. And I'll do this quickly so you guys can check out. Okay? Inside atoms, we have protons, which have a positive charge, protons, which are positive, and electrons, which are negative. Right? So if I ask you, we already said you can tell if we have a carbon atom, you know it has 6 protons because carbon's atomic number is 6. So let's put 6 positives there. All right? Every carbon atom has 6 protons. If I say, how many electrons does a carbon atom have? Your answer is, I don't know. Because some carbon atoms have 6 protons, some have 10, some have 0. All right? So you cannot just look at the periodic table and know how many electrons an atom has. There's one instance that you can. If I tell you that that atom is neutral, if I tell you that atom is neutral, that means total charge of 0. Well, I know there's 6 positives from the protons, so if I'm going to have a total charge of 0, I'd better have 6 negatives also. That means 6 electrons. So if the atom is neutral, I know the number of electrons must equal the number of protons. Okay, if I tell you the atom is neutral, the number of electrons must equal the number of protons. If you don't know that it's neutral, you have no idea of how many electrons it has. Okay?
Okay.
Actually, I was going to send a PDF, but now that you mention it, I can send a Microsoft Word file. Good point for Angela. Okay. So does everybody understand that? So the number of the number of electrons in a neutral atom is equal to the number of protons, which is equal to the atomic number. I'll say that again. The number of electrons in a neutral atom must be equal to the number of protons, which is equal to the atomic number. Okay? Any questions on that? All right. For you guys that got to check out, I am recording this. If you need to check out, go ahead and do your math class, because I'm recording this and I'll post it. Right? So you can look at the end, the things you're missing here. If you need to go to your math class. Okay?
Where are you gonna post the video at?
Probably on YouTube, because right now I don't know how to do it on, and I'll give you the link. I'll give you the link on YouTube. Right now I don't know how to post stuff on Blackboard. I probably won't learn that until this weekend. Okay, so if you need to go to your math class, go ahead. But remember, we were supposed to have a lab class from 6 to 8:30. Okay, so one more thing. Now that we know the number of electrons in a neutral atom equals the number of protons, now we can talk about those Roman numerals. All right, so I'm going to bring that back up. All right, here we go. All right, here we go. So we have these Roman numerals only for the representative elements, S and P block, in the green and the yellow, S and P block, the representative elements. So what's the significance of the Roman numerals? Okay? Well, we know there's protons and electrons in atoms. And you should know from middle school, and we'll talk more about this later, but it's been a while probably for most of you, the protons are in a tiny nucleus in the middle of the atom, and the electrons are orbiting. So the protons are in the nucleus, like the sun in the solar system, and the electrons are like the planets. That's, to a crude approximation, that's how we can view an atom for right now, okay? Although in reality, it's nothing like that, but that'll serve our purpose for right now. So the electrons are orbiting the are orbiting the nucleus, orbiting the protons, okay? Now, just like some planets are closer to the sun and some planets are further away from the sun, it's the same with electrons. Some electrons are closer to the sun, some are closer to the nucleus that contains the protons, some electrons are further away, all right? And next week, we will learn how to draw atoms, all right? But for right now, suffice to say, right? So you're going to write this down. This is the second most important thing we are saying today, right? So I'm going to say it slowly and I'll say it several times. So you should skip a few lines in your notebook. Skip a few lines. The number of valence electrons, and I'll say what valence electrons are in a moment. I'll write the word valence up here on the board. Let's unshare here. The number of valence electrons, V-A-L-E-N-C-E. This is a Greek word, an ancient Greek word. The number of valence electrons, I'll give you a chance to write that down. The number of valence electrons, get my back scratcher here. The number of valence electrons in a neutral representative atom. The number of valence electrons in a neutral representative atom. The number of valence electrons in a neutral representative atom. Okay, is equal to the Roman numeral group number. And I'll say that a few more times. Right? The number of valence electrons in a neutral representative atom is equal to the Roman numeral group number. The number of valence electrons in a neutral representative atom, is equal to the Roman numeral group number. Do I need to say that again? Don't hesitate to speak up. Do I need to say that again? All right, we're good? Now I'm going to bring that periodic table back up again.
I'm probably going to head out to work now, so I'll watch the rest of the video later.
Okay, that's fine. And I will email the assignment. Now, let's take a look
All
at
right.
it. Now, what are the valence electrons? We haven't said what those are. Well, just like I said, some electrons are closer to the nucleus and some are further away, just like some planets are closer to the sun and some planets are further away. The valence electrons are on the outer edge of an atom. Okay, they're the ones important in chemistry because they can move from one atom to another atom during a chemical reaction. So these are the electrons chemists are interested in, are the valence electrons. Chemists aren't interested in the other electrons. All right, so chemists would not be interested in like Venus and Mercury and Earth. They would be interested in the outer planets, Uranus and Neptune. Okay, so the valence electrons are on the outer edge of an atom. The outer edge of an atom. Okay, so we can see. Now again, you should put boxes and a star around that. All right? Now, let's take a look at our periodic table here. So if I ask the question, how many in a neutral oxygen atom, how many electrons are there? Anybody? In a neutral oxygen atom, how many electrons?
Just 8.
8. How many of those 8 electrons are valence electrons?
6.
6. Now, there is going to be one exception to this statement I just made. The number of electrons in a neutral representative atom, sorry, the number of valence electrons in a neutral representative atom is equal to the Roman numeral group number. Except for, I almost forgot the exception. So you got to put this exception down. I'm sorry if you already put the box around it with the stars. Except for helium, which only has 2 valence electrons. Except for helium, which only has 2 valence electrons. And we'll make that clear in a moment. We'll make that clear in a moment. Let's just spend a few minutes here doing a little bit of oral drilling and make sure everybody understands this. Okay? We only have like 5 people still with us. Okay? Okay, so let's look at potassium over here, number 19. What's the atomic number of potassium?
19.
19. How many protons does every potassium atom have?
19.
19. How many of those 19 electrons has 19 protons? If it's a neutral potassium atom, how many electrons does it have?
19.
19. How many of those are valence electrons?
1.
1. Okay, I'm going to do another one. Now, I'll do this one. I just want you to see how many questions you should be able to answer for any element right now. Let's look at bromine number 35 over here in the yellow. Right, bromine number 35. I'm going to ask, all right, what's the element, bromine? What's its atomic number? 35. What's its atomic mass? 79.904. If it's neutral, how many electrons does a bromine atom have? 35. What's its period number over here? 4. What's its group number up here? 17. We said if it's neutral, it has 35 total electrons. How many of those 35 electrons are valence electrons? Well, here's the Roman numeral group number, 7. 7. Is bromine a metal or a non-metal? Well, if I drew that line, it would be to the right of it, so it's a non-metal. Right? So we can, is it naturally occurring? Yes, it is. Anything from 92 and under is naturally occurring. Right? Will bromine conduct electricity? The answer is no, it's a non-metal. It will not conduct electricity. Right? Is it a good conductor of heat? No, it's a non-metal. Let's look at number 13, aluminum. Right? We know aluminum is a metal. Right? So it conducts electricity. It's in period 3 and it's in group 13. How many protons? 13. How many electrons does an aluminum atom have?
9.
How many electrons does an aluminum atom have?
I'm gonna guess 13.
He didn't say neutral.
Right, I did not say neutral. So you would say, I don't know. I don't know. You need to give me more information. If you want to know how many electrons, you need to give me more information. In other words, you need to tell me it's neutral. Very good, whoever said that. Was that Lucas? Very good, whoever said that.
There's someone else who said it too.
Okay. So now if I tell you it's neutral, then how many electrons does the aluminum atom have? If I tell
13.
you, how many?
13.
13. And how many of those are valence electrons?
3.
3. Right? Should we do 1 or 2 more, or are you guys okay with this?
Let's do a couple more.
Couple more. Now, notice in D and F block, we don't talk about valence electrons. There's no Roman numeral group numbers. So I will only ask you about valence electrons for the representative elements, S and P block. I think on the assignment, it might ask you, what does valence mean in Greek? What does valence mean in Greek? The answer is to be strong. To be strong. Valence in Greek means to be strong. So there's our three definitions: periodic, inert, and valence. Valence, right? Now, later in the course, we'll talk about covalent bonds, and that's where valence electrons from different atoms come together to form a strong bond. So this is why whatever scientists came up with this term for these electrons, you chose this term valence. Okay? You know, back in the day, if you wanted to be a scientist, you had to know Latin and Greek. Nowadays, if you want to be a scientist, you got to know English. And I would imagine 50 years from now, you'll probably have to know Chinese. All right. So we're going to do a few more. Again, if you feel comfortable and you want to check out, that's fine. Let's look at number 15. Oh, before I forget, let me talk about helium here. Right? Let me talk about helium. Why is helium an exception? Well, let's ask this question. How many protons does a helium atom have?
1.
Say again?
1.
1. Hydrogen has 1.
Oh,
Helium
sorry, I
has
was looking at the wrong one. Has 2.
2. It has 2 protons. Right? Do we see? Helium's over here in the upper right-hand corner. Atomic number 2. If it's neutral, how many electrons does it have?
2.
2. So we have 2 positives and 2 negatives, right? That makes it neutral. Add up to 0. Now, what Roman numeral group number is helium in?
8.
8. So you would think it has 8 valence electrons, right? But how can it have 8 valence electrons? It's only got 2 electrons total. How can 8 of them be valence? For an analogy, let's suppose I have 2 coins in my pocket, and I say to you, how many quarters do I have in my pocket? It would be ridiculous if you said 8, right? How can I have 8 quarters in my pocket if I only have 2 coins in my pocket? The same with helium. How can it have 8 valence electrons if it only has 2 total electrons? So here's that exception for helium, right? That exception for helium, right? Now, let's go back and do, oh, I should have unshared the screen here, right? 2 protons, 2 electrons, right? It can only have 2 valence electrons because it only has 2 electrons total. There's no way you can have 8 valence electrons. Someone should have said something to me there to unshare the screen. All right, let's go back to that periodic table here. All right, and let's look at strontium number 38 here in the green. All right, so its atomic number is 38, right? How many protons does every strontium atom have?
38.
Louder, you gotta speak louder.
38.
38. Every strontium atom has 38 because its atomic number is 38. How many total electrons does a neutral strontium atom have?
38.
38. Right, it has 38. So of those 38 total electrons that a neutral strontium atom has, how many of them are valence electrons?
3.
Louder?
3.
We're getting 3 from. Look at the Roman
2.
numeral group. Yeah, the Roman numeral group number
Oh,
is
sorry,
2.
2.
The Roman numeral group number is 2. Okay? Let's look at number 15 over here in the yellow. Right? Now, here, I'll tell you what, I'm going to do this one. Again, let's look at how many different questions we should be able to answer right now. What element is it? Phosphorus. What's its atomic number? 15. Right? So that's the first one. What's the atomic number of phosphorus? 15. What period is phosphorus in? 3. It's in period 3. What group is phosphorus in? 15. That's 3 questions. What block is phosphorus in? It's in P block. 4 questions. Is it representative or transition? It's representative. That's 5 questions. Does it occur in nature? Yes. That's 6 questions. Is phosphorus a metal, a nonmetal, or a metalloid? It's a nonmetal. Is it nonmetal or metalloid? I believe it's a nonmetal. Right? So that's 7. It might be a metalloid. I'd have to look. I believe it is a metalloid. So that's 7. Will phosphorus conduct an electric current? No, it will not. It's not a metal. Okay, so we said it has 15 protons. How many protons does every phosphorus have? 15. That's 9 questions. How many electrons does a neutral phosphorus atom have? 15. That's 10 questions. And then the final question, number 11, how many valence electrons does every neutral phosphorus atom have? Well, it's in Roman numeral number 5. So it has 5 valence electrons, right? 5 valence electrons. Okay? Everybody see? So right now you should be able to answer like 11 questions. All right, so do we have a volunteer? We don't have a volunteer? Come on, somebody volunteer. All right, Lucas is going to volunteer. Lucas, let's look at number 36. Actually, there was one more question we could have asked. There's 12 questions, so I'm going to ask Lucas 12 of them. So Lucas, we have krypton. What's the atomic number of krypton?
36.
36. What period is krypton in?
4.
4. What group is krypton in?
18.
18. Very good so far. Is krypton, what block is krypton in?
P block.
P block. Is it representative or transition?
The representative.
Representative. Does it occur in nature?
Yes.
Yes. Is it a metal, a non-metal, or a metalloid?
Non-metal.
Non-metal. How many protons does every krypton atom have?
36.
36. How many electrons does a neutral krypton atom have?
36.
36. How many of those are valence electrons?
The 8.
8. Will krypton conduct an electric current?
No.
No. That's 10 questions. Let's see. Is krypton an alkali metal, an alkaline earth, a halogen, or an inert gas, or none of those?
It's an inert gas.
It's an inert gas. Very good, Lucas. Very good. I know she had to look up a few there, but that's okay. We have another volunteer. We have another volunteer. Come on, somebody volunteer. You gonna make me pick on somebody? All right, Angela. Trying to hide there, Angela. You ready? Tilt your screen there, Angela, so we can see your face. There you go. There you go. What do you want to hide that pretty face for? All right, let's go, Angela. All right, you have number 12. Oh, sorry, magnesium over here in the green. Okay, you have magnesium. What? Uh-oh, what did I do there? Okay, there we go. What's magnesium's atomic number?
12.
12, that's the first question. What period is magnesium in?
It is in period number 3.
No? Oh, sorry, yes. What group is magnesium in?
Group number 2.
2. Very good so far. What block is magnesium in?
S.
Say again?
S.
S. S is correct. So if it's in S block, does that make it representative or transition?
Honestly, I don't remember.
It's representative. S and P block are representative. Okay?
Okay.
Does magnesium occur in nature?
Yes.
Yes, anything under 93, 92 and under. So it occurs in nature. Is it a metal or a non-metal or a metalloid?
It is. Non-metal?
No. Remember, we drew that line here. Look at your screen. If we draw this line here, everything to the left of it is a metal. Everything on this side is a metal except for hydrogen. All right, now
Gotcha.
let's get to
Yes.
the important parts here. All right, what's the atomic number of magnesium?
12.
12. So how many protons does a magnesium atom have?
12.
12. How many electrons does a magnesium atom have?
I don't know.
Right,
need more
you
info.
don't. Okay, well, how many electrons does a neutral magnesium atom have?
12.
12. Very good. And how many of those 12 electrons would be valence electrons?
2.
2, because it's a Roman numeral 2. Right? Very good.
Right.
Very good. Anybody else? Do we need to do another one? I think Joseph wants to do one. You ready, Joseph?
I'm good. I got
You're
it.
good?
I'm ready to rock and roll. I'm ready to do this assignment.
All right. You want to run through one here? This will be the last one here. All right. We ready?
All right, let's do this.
All
Yeah,
right.
let's knock this out.
Okay. Let's look at number here. Indium. Very soft metal. You could scratch it with your fingernail. All right. You ready?
Okay.
All right. What's his atomic number?
It's 49.
49. What period?
This is in period number 5,
And group number?
13.
What's its mass?
It is 114.818.
Is it a metal or non-metal or metalloid?
It's a metal.
Metal. What block is it in?
It's in P block.
P block. Will it conduct an electric current?
It will.
It will. How many protons does an indium atom have?
Total of 49.
49. How many electrons does an indium atom have?
That depends. I don't know.
Right. Don't know. Okay. If it's neutral, how many electrons?
49.
49. How many of those will be valence electrons?
3.
3. And one last question. Done great so far. One last question. Is it an alkaline metal, alkaline earth, halogen, or inert gas, or none of those?
It is none of those.
None of those. Remember, that group classification is the extremes. 2 on the left, 2 on the right, in alphabetical order. Okay, are we good here? All right, I'm going to let's see. All right, I'm going to stop recording. I'm going to email you the assignment, okay, as soon as we're done. I might actually email you 2 of them, okay? Now, let's talk about, so you're going to email me. I will email you the Microsoft Word file. Then somehow get it back to me. I will tell you, if you can get it back to me, the sooner you get it back to me, the sooner I can grade it. I would prefer that you don't turn it in Monday. Because if you turn it in Monday, I'm back at the high school. The sooner you can get it to me, for one thing, I can print them at the high school Thursday or Friday for free. If you get it, you should try to do these while this stuff is still fresh in your head, for one. Try to do it while it's still fresh in your head. But again, the sooner you get it to me, the sooner I can grade it and get it back to you. Okay? I will send you those as soon as we're done here. I have them on my computer and I'll just email them to the whole class. Any other questions? All right, so I'm going to stop recording and I will send the link I will upload this to YouTube later tonight.
Wait, Nanny, I thought we were gonna do a lab.
Not tonight, we won't.
Oh, this is Jack, by the way. I didn't leave. I stayed.
Wait, let me stop